For a premixed frame, in the beginning, we try to use the so-called one-dimensional frame model to let you know the flow structures near the premixed frame, starting from very far upstream. Then we approach to the heating zone, then go to the reaction zone. Then later we are move into the downstream high temperature zones, and by experimental observation, especially we use the flood frames in the stagnation point flow to give you some confirmation on the velocity distributions and also temperature distribution for a given flat planar frame. And actually, this flat frames in the stagnation point flow actually is has a similar effect, a similar flow structures compared with that for the one-dimensional flow, one-dimensional premixed frame. And this is the one example and easier to be exempt from the laboratory scale experiments. Now we move to the next one. This one, so-called the Bunsen frame, Bunsen premixed frame, and we already introduced and try to give you the fully understanding by changing the mixing ratio for the fuel from 100% up to the 12%, maybe even lower, go to the lean mixing conditions. Then you can see those kinds of flame characteristics are changed completely with the flame color, with the flame length, and also the stabilization of the premixed frame. Now we need to know how can we have these kinds of flame characteristics in this Bunsen burner. Actually, Bunsen burner is usually can be described as the burner to produce the jet flow. Then when we want to study the combustion characteristic in that flow, you need to have some basic understanding on cold flow structures. I hope you, I want to mention again, especially when you go through the combustion study, in the beginning, you always need to examine the flow structures, flow structure better, because when you know the cold flow structures, then those kinds of ideas based on the combustion science can be applied to the cold flow structure. Then usually you need to have some examination on the flow structure for your cold flow situation. Then by knowing some concept from combustion science, then you can identify where we can have the frame exist or frame stabilize in such a flow region. Okay, that means the preliminary study on the chemical reaction application, you need to go through the cold flow study. Now let's go to examine the flow structure for a given free jet. Okay, this is a typical example. I took these pictures from the Canoni's book and Introduction to the Combustion Phenomena. Actually, this is the old one, but there is a new version you can find. This is a very fundamental book to be used to understand the combustion phenomena. Okay. Now think about the flow structure illustrated in this by these figures. We assume there is the hole. Okay, there is a small hole here, or you can assume that this is a port of the burner. Then the flow will coming out, and the diameter hole is defined by di, and the injection velocity is assigned as the ui. And at this point, the cross section with the A, that means that just the exit plane of your burner. In this case, since we assume you can have some arrangement from the experiment, assume here you can have some screen or honeycomb, try to reduce this big hole to very tiny small hole, and push all your flow follow those small hole and inject it out. Then you can produce the so-called uniform velocity distribution profile at the exit plane. The velocity distribution, especially in this case, because we force all the flow moving along the axial directions, here origin, we make it located at the center of the exit plane of the burner, and followed by the axis along the vertical axis. and the radial axis, you can assume y is radial coordinates, or you still can assume this port is the slot. Okay, that means that there is a long length point to to our screens. Okay, and this is they will give you the same flow structures can be described. Now, by this point, if you try to plot the actual velocity distribution at a different cross section A at the axis plane, then move a little bit downstream, cross section B, cross section C, cross section D, until to the very far downstream side, cross section F, and we try to describe the variation of actual velocity distribution for the first cross section A here. Since we are dealing with the velocity distribution just at the axis plane, and I just emphasize you can assume at this axis plane the actual velocity are uniformly distributed across the cross section of the axis plane. From the experiment, actually, you can try to do to make it be possible by using the honeycomb or screen with a small hole to restrict all the flow will flow individually to small hole. Then you will produce the uniform velocity profile just at the axis plane. Okay, this is a velocity distribution at the axis plane. This just like a head shape. Okay, at different radial distance, all the actual velocity are the same. Okay, are the same. Okay. Now you can think about when you have a jet impinging out. That means in this region, the center region of a jet with the higher velocity compared with the environment. Now the environment we assume it is stagnant. Stagnant, and that means the no velocity. Now you can figure out there is a high velocity inside of the center region of the jet. That means the pressure will be reduced, right? When you have a large velocity, flow velocity, usually the collision of droplet of a molecule will be suppressed, and all the gaseous molecule will move along the flow convections. Then this pressure inside of the flow will be reduced. But in the outer surroundings, the velocity is equal to 0, and the pressure remains as its usual is atmospheric pressure. Higher, this pressure is higher than that inside of the flow, then this pressure gradients will push, or we call suck, the outer gaseous species, gaseous molecule move into your jet. Okay, move into a jet. That means that at the boundary, for example, for the cross section A, this corner will start to have some interactions with the molecule outside of the surroundings, and they will lose their actual momentum and try to, because there is some expansion, those actual momentum will try to divert certain amount of momentum into the radial distance. Then radial momentum is produced gradually. Here you can see for the cross section A, since we just coming out, all the molecules, all the gaseous molecules just coming out, they can maintain the same actual velocity at the cross section A. But for the cross section B, you can see now we move a little bit away from the exit planes, and you can see the uniform the region for uniform actual velocity distribution become narrow, because there's some momentum is reduced and convert to radial momentum. Okay, they can have interactions with the outer gaseous medians. Okay, but you can see at the cross section B, they still have in the center region, the flow still retains their actual velocity are uniform, but region become narrow. When you go further, there is the final point. Gradually from cross section A move to the downstream side, you will find out the region of uniform actual velocity will reduce smaller. Final point they will reach at this point. This is the final point for the flow velocity. Actual velocity is exactly equal to injection velocity. when you increase the axial coordinates more, then there is no position to be possible to have the axial velocity the same as the injection velocity, which means in this sense they give you the so-called potential cone here. Potential cone means in this region all locations has the same axial velocity, and those axial velocity is the same as injection velocity. Okay. Now, why we say this is a potential cone, then I think that all students know what is the potential flow. Potential flow means there is the three assumptions be defined for potential flow. One is the invisible, the other one is the incompressible, okay, and then the other one is the what is the I? Invisible, incompressible, and in irrotation. Okay, that means that all the velocity, all the viscosity, all the shear force will complete neglected, and all the point that can retain the same velocity from the cross section A up to the final point. And here we call this as a potential cone. This is a very important flow characteristic you need to remember. Even in this flow situation, if you consider the viscous flow, there still exists the so-called potential cone. In this region, every point has the same axial velocity. I hope you remember this as an important point for this flow structure. When you go back to the stagnation point flow or opposite jet flow, I always emphasize why we can have a flat flange, because at that position, at that cross sections, for a certain axial point, axial positions, they have a uniform axial velocity. When you have an a uniform axial velocity, then you will have possibility to produce a planar flange, because a single value of flange speed will be balanced with the single value of injection velocity. Okay, this is the benefit for us to do the experiment just along one axial directions to do all the measurements and realize the whole flow structures for a given frame. Similar here, when you think about there is the uniform velocity distribution and belong to its value belong to the value from the exit plane, that means injection velocity in this region. Okay, we call this as a potential cone. But when you move to the downstream side continuously to the section C, you can see the axial velocity at the center line continuously reduced from the cross section C to D to E to F continuously, and you can find out the jet boundary extent from the small region at cross section B. This is a small region, but cross section C extend the jet boundary continuously to the very far downstream side. It is, has a very large extensions for your jet flow from the beginning. And when you try to measure the velocity distribution for the actual velocities, you can see the profile continuous change. The value of actual velocity at the center is continuous reduced, and they will expand to the radial directions. And when you use those kinds of non-dimensionalizations, you will find out, if you do the non-dimensionalization, means that you try to neglect the geometric effect, then you will find out after the F, or maybe after the E, after the F, this is a real velocity distribution. But when you do the non-dimensionalization, you will find out the velocity distribution will be the same. That means that the behavior is very similar to the so-called boundary layer flow, right? Boundary layer, when you are starting from the plate edge, then they build up the boundary layer flow. Inside a boundary layer flow, they will continue to change their velocity profile until certain distance. The non-dimensional velocity profile will become the same without change. At this time, we say we go to the so-called fully developed region, right? Flow go to the fully developed region. That means the viscous flow balance with the pressure-driven flow, then all the flow velocities that will retain their velocity profile. Then we say this is a fully developed region. Similar way for jet flow in a very far downstream, when you look at their non-dimensional velocity profile, then you will see the velocity profile do not change as you move further to the downstream side. Then we call this as a so-called fully developed region. And between the potential cone and the fully developed region, you will have an intermediate region. We call this as a transition region, which means that from the cross section, starting from the edge of the potential cone until maybe up to the E, cross section E, maybe move to the cross section B. In this region, basically, is a transition region. Okay, and now this is a typical flow structures. I hope you can understand. Now, based on this flow structure, you can think about how to define. If I ignite it, if I choose a premixture of mixing and air with a certain composition, that means the mixing ratio, then I apply it and ignite it. Where is the location of this premixed flame is interesting thing we need to determine. Okay, when you go back to see to look at the original figure I show you, there is the double flame in our flame transitions for your Bunsen flame, right? This is the final pictures. As I remember, the mixing ratio is around 14%. Then you will have a inner flame. This inner flame is a rich premixed flame. The outer flame is a diffusion flame. Now we think about how come we can you imagine why these two flames will sit at these certain positions? Now we go to the next slides. Okay, you can do the calculations from analytical results or numerical results, and you will find out the overall flow structures like this. And you can have a potential cone here. This cone, this perfect cone, tell you in this regions, all the points, okay, all the points will have the same actual velocity. Out of this potential cone, then you will try to find out there is a so-called iso concentration lines, iso velocity line, and also isothermal lines with some non-dimensional quantity. For example, this is an iso. We use this as a non-dimensional temperature representations, and this is a YF means if you assume this is a fuel jet, and we'll try to look at the mass fraction of fuel exists in these regions. And you use U for different for the actual velocity for at different positions divided by the injection velocity, then you will have a non-dimensional quantity. If you do all these kinds of non-dimensional normalizations, and you will find out the results from the Navier-Stokes equations. Analytically or numerically, you will find out there is some value. For example, this is a 0. 0 means if you look at U divided by UI, 0 means you do not have the actual velocity, right? Which means the actual momentum of an initial free jet will lose completely at this line, and this line basically can be defined as the boundary of your jet, right? And you remember we have a free jet initial with a certain actual momentum that injecting out to the stagnant environment. Stagnant environment, the flow do not burning, or do not moving. That means that they do not have a velocity. And this tell you those kinds of actual momentum will continuously reduced. Okay, from the initial is 1, U divided by UI is equal to 1, then 0.9, which means they just have a 90% actual velocity left, 80%, 0.8, 70%, 60%, 50% move to the 10%. Okay, here that means that those kinds of iso velocity line tell you the jet is extended to the very far downstream and lose their actual momentum gradually, but they expand their the jet boundary continuously to enlarge it into the downstream side. Similar way, you can see there is the temperature profile, okay, isothermal, which means you will see 0.9 means the temperature is relatively high, okay, then they will continue reduce from the from 0.9 up to 0.1, the temperature will be reduced because all the hot flow will move to the downstream side, okay, and the mass fraction, if you have a few, and they will continuously diffuse out, okay. By looking at this flow structure, actually, I need to mention, typically, if you try to calculate or analytically describe all these kinds of velocity distribution, you can have this very nice composition line, velocity line, or isothermal line. They are just combined together with a certain basic assumption. If you are interested in, you can go through those kinds of formulation from the Canoni's book, okay? Basically, they are dealing with the mass, momentum, and energy conservations in a jet flow. You can try to learn it by yourself. Anyway, I just tell you the results. And this result give you a very interesting observation. Now, if this is the cold flow structure, what do we do to think about when you ignite it? Where is the premixed frame? Where is the diffusion frame? Now we try to give you the some comparison here. When you look at these three figures, the left-hand side tell you we have some cold flow study, and you can see there is the potential cone, and also there is some iso velocity line, iso temperature line, and also iso concentration line. Now, when you refer to our experiment on frame transition from diffusion frame to the premixed frame, as you know, if you have a diffusion frame, means we just inject 100% fuel coming out. That means that those fuel will move from the exit plane or burner continuously to the downstream side by the flow convection, right? And the combustion, or we call this the burning, occurs only at the diffusion frame, which means that this interface between the fuel and the oxygen in the surrounding, right? Now you look at this jet, where is the fuel region? Basically inside of your free jet, right? Because free jet contains fuel 100% only. Where is the oxygen? Oxygen exists in the outer region. Okay. Now where is the boundary? Definitely, we will figure out. The boundary is defined by the free jet boundary here, right? 0.0. That means the flow velocity or concentration will reduce to 0 here. This is the maximum extent of the influence coming from the free jet. Then you expect this could be a boundary to separate your fuel and oxygen, right? And if you have a chance to burn, that definitely you will think about your flame. The diffusion flame will exist very close to the jet boundary. But in our experiment, they may not exactly just sit at this 0, the interface and the jet boundary. They may shift a little bit to the fuel side or to the oxygen side, depend on the diffusion trend from the oxygen side and the fuel side. You remember when we have a diffusion frame here, right? This is I just plot it to represent the shape of diffusion frame, and the orange to the yellow color represent the typical color for diffusion frame. And you can see this diffusion frame will separate the fuel inside of the jet and also the oxygen in the outer environment. They are separate. And this diffusion, the location of your diffusion frame is very closer to the jet boundary, but depend on the diffusion trends from the outer surrounding. For example, in normal case, we burn the fuel jet in the air environment, then oxygen will diffuse to support your diffusion frame and to balance with the diffusion of the fuel from the inner region, right? The diffusion transfer, they balance, then your diffusion frame will sit here. But in case you try to increase the oxygen concentration in your environment from 21%, increase to 30%, 40%, that means the diffusion strength from the outer region becomes strong. When you diffuse more oxygen into your premixed friends, into your diffusion friend, that means you need to have more fuel to diffuse to balance it to finish the combustion, right? And by this kinds of diffusion transport balance, your diffusion friend will push closer to your center region. They were more closer to the center, the axisymmetric axis. Okay, this is basically tell you the location of diffusion friend is determined by the balance of the diffusion transport of oxygen from the outer region and the diffusion transport of fuel in the inner region of your jet. Okay, this is the first one. First point I want to mention. Where is the diffusion friend? Is basically determined by the separation of fuel and oxygen. If there is the interface separate the fuel and the oxygen, then that interface could be treated as the location of a diffusion frame, but the location is not completely exactly equal to the interface. They have some kinds of deviation from the interface, okay, the jet boundary. The second thing I want to mention here, why I used a blue color to represent the base of your diffusion frame. As I mentioned before, when you have a jet impinging out initially, they do have a larger axial momentum coming out. The velocity is very high, then produce a lower pressure. And in this case, the outer pressure compared with the inner pressure to produce a so-called pressure gradient. This pressure gradient will push the outer air be sucked as a driving force to push your outer flow. Outer air will move to closer to your jet. And by this kinds of movement, actually we call this the so-called suction, suck in. We suck air closer to your diffusion frame. That means that you supply more oxygen, more efficient oxygen to approaching to your diffusion frame. Originally, the burning of your diffusion frame depends on the diffusion transport of fuel inside of your jet and the oxygen outside of the outside boundary, right? Now you have additionally assistance by flow convection push your oxygen to be move closer or supply more to your frame surface. Then they will enhance their reaction because you have more oxygen. And those more oxygen diffuse in or suck in, they will convert the carbon reticle. You remember in this region, since they all in this region, we all have only those fuel only, right? It contains some carbon particles, molecules decompose from the original fuel. Then there are so many carbon, and when they closer to the diffusion flame, they require more oxygen to be react. Then they produce the carbon monoxide or carbon dioxide. Okay, and this is the reason why the flame color become blue, because we have additional support from the pressure gradient to drive the oxygen molecule to react with the fuel diffused from the inside. And the other point is, in this region, the axial velocity is stronger than that in the downstream side. That means that they will drive, they will flow, they will push those kinds of carbon particle to the downstream side. Okay, the residence time in this region is less, then they can move to the downstream side with some accumulation with the other one. Then the combination or collision of molecule, carbon molecule together, they will produce a larger size of particles. Then you will have a very intense, bright yellow color in the downstream side. Near the base of your diffusion flame, usually you can see there is the blue color. But remember, at this state, all the flame is attached on the burner edge. Okay, no oxygen can be penetrated into the interior region of your fuel jet. Okay, now we move to the last point we studied from our frame transition in the beginning. And you figure out there is the double frame, right? As I mentioned here, there is the double frame just like this. The inside frame is a rich premixed frame. The outer frame is a diffusion frame. And then the typical plot can be shown by here. Here there is the a rich premixed frame. You will see there is a very small, and usually they give you the idea this is a cone, right? It's not a perfect cone because they extend a little bit longer. Later on, I will show you. Yeah, here this is the perfect cone, right? And for this kinds of burning, actually tell you the premixed frame is very close to the potential cone. And I mentioned potential cone has a very unique features because at any location inside of potential cone has the same axial velocity. Then this unique feature to give a possibility to produce the perfect cone premixed frame exists for the Bunsen burner. But in this case, I need to mention again why you can have a perfect cone because in this case, I already assume the injection velocity, okay, is uniformly distributed along the cross section of your burner. But if you do not use any technique try to make the velocity uniform, for example, you just let it open, then you understand that if you have a long tube flow moving in at the exit plane, actually the velocity distribution will become so-called the fluid bed flow shape, right? Then this is different from the uniform flow distribution. Then frame shape will change a little bit, but anyway, the frame length is always small, very closer to the potential cone. And here this is typically to tell you the location of your premixed frame. Later on, I will give you some more introduction to the location determination for the premixed frame. But for the diffusion frame, here you can see now this blue frame move to the inter region of your free jet, right? Why? As you remember, this is a rich premixed frame. Rich premixed frame means fuel is rich in the beginning, and actually they will most of the fuel will be completely consumed with the with air, right? With the oxygen inside of air, but they still have excess fuel left in the downstream side, okay? Because this is a rich fuel frame, rich premixed frame, and those fuel actually is excess fuel is not equal to original rich fuel. That means the amount of fuel is less compared with the original fuel concentration, which means that their diffusion rate, diffusion strength is much weaker compared with the purely diffusion frame. In this sense, the diffusion of oxygen from the outer becomes stronger than they will the oxygen molecule can cross from the original expect interface boundary to the interior regions to meet the fuel. Then the diffusion frame will move to the flow structure predicted by cold flow to sit closer to the premixed frame. Okay, and the frame length becomes smaller for the premixed frame. This is the typical locations for your diffusion frame, as I mentioned. When you look at here, right, and you remember when you go back to the original condition, 100% methane, the frame length is pretty much high. It's around, I remember, it's a 50 centimeter, right? In this case, they just have less than 20 centimeters. That means a diffusion frame, the length of a diffusion frame reduced very much, okay, because in this region, the fuel depth basically is the excess fuel is a small amount. They do not have a strong diffusion strength. Then the oxygen need to diffuse close into the flow boundary of your jet, then to meet the fuel inside of the interior region. Then you can have the location of a diffusion frame. Look at this these two frames. I change color. Okay, here for purely fuel, then there is the yellow color. But for the right one, I completely use the blue color since because the fuel is less. therefore the accumulations of carbon particles are less. They do not have a very big one carbon particle and has a possibility to show their high illuminarities, and they will give you the blue colors. Okay. But here, this is also tell you the length of the diffusion flame still long, okay, because basically they are closer to the jet interface for the diffusion balance of a fuel and oxygen. But for the premixed flame, actually they are balanced at a certain positions. The supply velocity should be balanced with flame velocity, as I described in the one-dimensional premixed flame or the flat flame stabilized in the stagnation point flow. Later on, I will tell you how to make the decisions to look at the velocity balance between the supply velocity and also flame speed. I will describe in more detail in next part.